This video is part 2 of a 3-part series and will discuss the ESP32 code that was used to develop the LotBot Jr prototype. The code may not mean much to you unless you saw the introductory video on my LotBot robotics channel named LotBot Jr, an ESP32 Raspberry Pi Node-RED MQTT Wi-Fi access point development project. Part 3 will discuss the Node-RED project code in detail. Now let's look at the code. Before I begin, I just want to say that there are many ways to develop code to accomplish a process. The purpose of this video is to explain the code for the ESP32 that was used in the previous video about the LotBot Jr prototype. The Wi-Fi include and the pub/sub client include become part of your library using the Arduino IDE manage library function and installing the libraries associated to the manager's search filter for these includes. There are many tutorials that talk about the ESP32 pins used as PWM pins to control servos. There are examples of how to install the ESP32 LED include on the internet. I am going to show you how I used it in this tutorial. The ultrasound trigger pin is 21 and the echo pin is 18. Pins 32, 33, and 25 are used for the common cathode RGB LED. The variable duration is set up as the time in microseconds a sound wave travels when sent from the ultrasound sensor trigger to a reflected obstacle and returned to the receiver identified as echo. The distance in inches variable is the computed distance in inches that the sound wave traveled. The LR variable indicates if the server connected to the ultrasound is moving to the left or to the right. The use of the LR variable was to include some function that is in the LotBot Robot that was the subject of my first 2 videos on my channel. In LotBot, the ultrasound sensor is connected to the Raspberry Pi and not an Arduino, which in the prototype is replaced by the ESP32. The solution that is solved in LotBot is when a robot is heading directly for an obstacle. It can back up and move to the left or right. However, if it is moving to an obstacle, say at a 30-degree angle on its right, you would want it to back up and move to its left to get away from the obstacle. If it is coming in from a left at some angle, you would want it to back up and move to the right to get away from the obstacle. However, if the robot is moving at an angle and the sensor was pointing straight ahead, the sound wave would angle off the obstacle and not return to the sensor. Mounting the sensor on a servo allows the sensor to identify obstacles at various angles to the robot. 2 problems still exist. The first is to ensure that the movement of the servos don't cause the robot to hit the obstacle before the sensors could identify that it exists. I just used physical tests to see how fast the servos should be, which worked for me. Depending on the servos you use, you may have to alter the constants values that I use in this code. The second problem would use the LR variable. The LR variable holds a L or an R to indicate if the servo was in a position on the right when the ultrasound sensor found the obstacle or on the left. I started the code in this module but never finished it as the ultrasound sensor is connected to the Raspberry Pi for the LotBot Robot. The Raspberry Pi Wi-Fi access point ID and password are set to RPI Wi-Fi AP. I need to tell you why I am using an access point not connected to the internet. There are 2 reasons. The first is that the MQTT messages require Wi-Fi. The second is that the LotBot Robot in my second video was changed to communicate between the Raspberry Pi and two Arduinos using Bluetooth instead of a serial cable. Since I require a local Wi-Fi access point, it makes sense to change the communications between these microcomputers from Bluetooth to Wi-Fi and use the MQTT messages. This still allows LotBot to work and not be tied to a specific internet Wi-Fi. The duty cycle has to do with the movement of the sensor servo. The MQTT server is on the Raspberry Pi, and I set that IP address up to 192.168.79.21, and since it is a local Wi-Fi access point, it is secured from the access from the internet. The MQTT port is set to 1883 as recommended by MQTT documentation. ESP client is set up as a Wi-Fi client. A publish subscribe MQTT client is set up to use the Wi-Fi client ESP client. I'm sure you know this, but not knowing my audience and not wanting to leave anyone behind, just a few words about the program structure. Arduino-like modules like the ESP32 C++ program are structured to have a setup routine and a loop routine. The MQTT processing requires a callback routine to handle the incoming MQTT messages. The setup routine handles setting up initial conditions and values, and the loop routine is the ongoing process of the program. The beginning of the setup routine sets up 3 channels that I decided to use of the 16 available. Channel 1 is for the servos on one side of the robot, and channel 2 is for the servos on the other side. If you have all 4 servos moving in the same direction for each servo, then the robot would be moving in a circle. So servos on channel 1 need to move in the opposite direction from the servos on channel 2 in order for the robot to move forwards or backwards. Channel 3 is used to move the servo connected to the ultrasound. The frequency can vary, but 50 works for me. I used 8 bits for the resolution, but I've seen examples that use 16. Pins 4 and 5 are set to channel 1 to control 2 servos to turn wheels. Pins 16 and 17 use channel 2 to control the other 2 servos and wheels. Pin 22 uses channel 3 to control the servo turning the ultrasound sensor. Writing 0 to the 3 channels stops the servos as an initial state. Pin mode can set a pin to input or output. The trig pin is set to output as it sends out a sound wave. The echo pin is set to input as it receives the sound wave. The RGB pins, red, blue, and green, are set to output to change the LED to the required color. The digital write sends a voltage to a pin. At startup, you may recall from the initial LotBot Jr video that the LED is red. So the voltage for the red pin is set high and the blue and green pins are set low so not to mix the colors. The baud rate that I have seen most often for the ESP32 serial display is 115,200, which is set to begin this serial session with a display. The display is a way to debug a program, but is not required when the robot is detached from the computer using the Arduino IDE. You probably know this, but once the program is written to the ESP32, it remains until another program overwrites it. The program is then delayed 5,000 milliseconds or 5 seconds to let all processes be established. The Wi-Fi.begin starts a connection with the Wi-Fi access point using its ID and password. The code then checks the Wi-Fi status to see if a connection was made, and if it was not, it will wait for 1 second, print a message to the serial display to say that it is still in process of connecting. The loop will continue until the Wi-Fi access point connection has been made. Once the connection has been made, a message indicating the connection has been made is printed to the serial display. Also, the red LED is changed to a blue LED. The code waits for 3 seconds to ensure all Wi-Fi connection code completes. Then the code starts a connection with the MQTT server using its IP address and recommended port. The MQTT callback routine is also set up. A message is printed to the serial display that the prototype is connecting to the Raspberry Pi MQTT server. The processing is delayed for 2 seconds, which is enough time for the connection to take place. If the connection completed successfully, a message is printed to the serial display that the ESP is connected to the Raspberry Pi MQTT server. The blue LED is changed to a green LED. If the connection is not made, then a connection error message is printed to the serial display. I have never seen the MQTT server not connected once the Wi-Fi access point was connected. The code then publishes an MQTT message for the LotBot topic that the ESP32 is connected. In the previous video for the prototype, I pointed out that this message was seen in the Node-RED debug display. The ESP32 then subscribes to MQTT messages for the LotBot topic. And that is the end of the setup routine. The program execution then starts with the loop function. However, my code was written with the callback function physically next, so I will discuss this as found in the code. When an MQTT message has been published that matches a topic, the MQTT server sends the message to all routines that subscribe to the topic. The callback function is called to process the message in this ESP32 program. The callback function gets the topic name in the variable topic, the message in the variable payload, and the length of the message in the variable length. The code builds a print line to be displayed on the serial display describing the message, including getting the payload in character format, and then prints the line. For my servos, using 25 for a channel spins the servos in one direction and 5 spins the servos in the opposite direction. If the payload is an F, meaning move the robot forward, channel 1 spins in one way and channel 2 spins the opposite, as explained earlier. A B for backwards would be just the opposite for both channels. For the L, both channels need to be coded with a 5 and both channels need to be coded for a 25 for an R. A 0 is coded for both channels to stop the servos. The way my channels work is dependent on the way I install the servos in the robot. You may get different results if you install your servos differently, but getting them to work correctly is just a matter of changing the values for the LEDC write commands. The loop function just starts at the top of the function and goes to the bottom and continues to loop through its code. The LEDC write to channel 3 is what turns the servo connected to the ultrasound. There is a 400 millisecond delay in the loop. The code checks to see if it is at the extremes in turning the sensor and changes direction when it reaches its limits. The position of the sensor is incremented or decremented by 2 that allows the sensor to check 11 positions for an obstacle. At each position, the trig pin is set to low for 2 microseconds and then high for 10 microseconds. The duration the sound wave took to return in microseconds is returned by setting the echo pin to high. The documentation says to divide the duration by 148 to get the number of inches the sensor is away from an obstacle. The 148 is derived from sound traveling at 340 meters per microsecond, and there is 39.37 inches to a meter. I did the math and came up with 147.68, which is close enough to the 148. The code checks to see if the sensor is within 20 inches from an obstacle, and if it is, the prototype stops for 2 seconds, backs up for 2 seconds, moves left for 2 seconds, and then moves forward. This is the code that I mentioned earlier that should determine whether or not the robot is coming from the left or the right at some angle. The check for greater than 2 inches is to eliminate some noise that I noticed that produced invalid results. The final client.loop is to keep the callback function active. This LotBot Jr prototype code is intended to be migrated to the LotBot Robot. The prototype does have a bit of delays that are not found in the LotBot Robot, as the sensor in the LotBot Robot is in a separate thread from the main flow in the Raspberry Pi, which supports multi-thread. Well, that concludes my discussion of the project ESP32 Code. I will be going through the Node-RED project code in the next video as part 3 video of this series.